chapter 9, a couple sections out of this chapter, we're looking at 9.1. We're going to talk about sequences. And the definition of our sequence is if we have an infinite sequence is a function whose domain is a set of positive integers. That means 1, 2, 3, 4, 5. No more fractions, no more decimals, no more radicals. All right? The function values a sub 1, a sub 2, a sub 3, a sub 4, a sub 5 are going to be considered the terms of the sequence. This will be the first term, second term, third term, fourth term, fifth term. So if the domain consists of the first n positive integers only, the sequence is a finite sequence. So this is very close to what we've done before. If you had the function f of x equals 2x plus 5, this is the same as a sub n equals 2n plus 5. So we just alter the notation here so we can see the difference. Here, x can be all real numbers. In a sequence function notation, n can only be positive integers. So if we were asked to find the first 5 terms of a sub n, you start with n equaling 1. We're going to substitute it in every place you see an n. So a sub 1 is equal to 2 times 1 plus 5, which is 7. When n is equal to 2, we're going to get a sub 2 is equal to 2 times 2 plus 5. That's 9. N is equal to 3. A sub 3 is going to be 2 times 3 is 6 plus 5 is 11. When n is equal to 4, a sub 4 is equal to 2 times 4 plus 5 is 13. And you probably notice the pattern that I'm increasing by 2 every time. That's because we're multiplying by 2 to a next bigger number. So I'm going to guess it's 15 for the next one. So when n is 5, all right, a sub 5 is 2 times 5 is 10 plus 5, 15. Sure enough, it works. That's the sequence of the first 5 terms for this sequence. Now, if we try to find the first 5 terms of, holy moly, a fraction here, a sub n is equal to a negative 1 to the nth power all over 2n plus 1. Well, we'll go through the same procedures. When n is equal to 1, we'll put 1 up here in the exponent position. We'll put 1 in for the n being multiplied by 2. And our a sub 1 will be, well, negative 1. 2 times 1 plus 1 is 3. When n is 2, now a sub 2 is going to equal a negative 1 squared, which makes this a positive 1. 2 times 2 is 4 plus 1 is a 5. When n is 3, a sub 3 is now negative 1 raised to the third power. That's 3 negatives. So this is now back to a negative 1. 2 times 3 is 6 plus 1 is 7. So what's happening in your numerator is you are getting alternating signs, negative, positive, negative. The next one's going to be positive. I see the same pattern in my denominator as we did in the last problem. Because you're multiplying by 2, we count by 2s. 3, 5, 7. So I'm going to guess the next a sub 4 is going to be 1/9. Yep, sure enough, there it is. Negative 1 to the 4th power is a positive 1. 2 times 4 is 8 plus 1 is 9. Then the next one's going to be negative 1 over 11. Yep, there it is. Negative 1 to the 5th, that's an odd number of negatives. That's negative. 2 times 5 is 10 plus 1 is 11. There's my first 5 terms of that sequence. Now, the other thing we can do is we can also be given a bunch of numbers and then determine the sequence. All right, so make a t-chart to find a pattern with the difference tests. So what does that mean? N is going to be 1, 2, 3, 4 because there's 4 terms listed. A sub n is 1, 3, 5, 7. So do the difference test of the second column. Well, 1 to 3 is increasing by 2. 3 to 5 I increased by 2. 5 to 7 I increased by 2. If this is the same after your first time doing this, that's called the first level difference test. This is a linear equation with a slope of 2. So my a sub n has to have a 2n in it. Well, if I go, okay, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, what do I need to do to this 2 to get to a 1? The 4 to get to a 3, the 6 to get to a 5, the 8 to get to 7. I need to subtract 1 every single time. 2 minus 1 is 1, 4 minus 1, 3, 6 minus 1, 5, 8 minus 1, 7. So put a minus 1 in your a sub n formula, and that's going to create those odd numbers, 1, 3, 5, 7. And sure enough, there's your numbers. It's going to work. All right, next example. The first thing I notice is we have alternating signs. Well, you saw in that previous example, when I started with negative 1 to the n power, my first number was negative. Well, now my first number is positive, then it's negative. So what we're going to do is we're going to put negative 1 to the n minus 1 power. So 1 minus 1 is 0. Any base to the power of 0 is 1 as long as your base is not 0. So we're starting out, we're going to put negative 1 to the n minus 1 power in our answer. Once you do that, you don't have to worry about the signs. Make a t-chart and keep the 2, 5, 10, 17 here. All right, so difference test. 2 to 5 increases by 3. 5 to 10 increases by 5. 10 to 17 increases by 7. Okay, this is not linear. I have to do the difference test again, and now everything is increasing by 2's. This is quadratic. This means I'm going to have n squared somewhere in my formula. So I'm going to make another column. A sub n starts out with n squared, so whatever we create up here, we'll move down here and multiply it after this. So I need to look, okay, here's my 1, my 4, my 9, my 16. What do I need to do to get the 1 to get to the 2, the 4 to get to a 5, the 9 to get to a 10, the 16 to get to a 17? I need to add a 1. And if we test it, sure enough, 2, 5, 10, 17, there's my numbers. And now if you do the alternating signs with this, you'll have that original sequence. So we'll take the n squared plus 1, put it in parentheses, and multiply it to this negative 1 to the n minus 1 power. Next sequence we're going to define is the recursive sequence. This sequence is a pain in the butt, because here, in contrast to here, if I wanted to say, go to this first sequence over here, and I wanted to find the 10th term, I just got to put a 10 in for n. Okay, 10 times 2 is 20 minus 1. It would be 19. In contrast to a recursive sequence, notice that the definition says where the next term in the sequence is determined by the values of the previous terms, not the n value. So if I want to find the 10th term of a sequence here that's recursive, you got to find the first, second, third, fourth, fifth, sixth, seventh, eighth, and 9th before you can find the 10th. Oy. So in my example here it says a sub 0 is 1. A sub 1 is 1. So they're starting off our sequence with a 1 and a 1. A sub n is equal to a sub n minus 2 plus a sub n minus 1. So when n starts at 2, that means a sub 2 is equal to a sub 2 minus 2 plus a sub 2 minus 1. Well, 2 minus 2 is 0. This is a sub 0 plus a sub 1. I'm taking these two terms, adding them together to find the a sub 2 term. That's a 2. Ay, ay, ay. When n is 3, all right, a sub 3 is going to equal a sub 3 minus 2 plus 3 minus 1. That's the a sub 1 plus a sub 2. All right, a sub 1 is 1, a sub 2 is 2, 1 plus 2 is 3. So I'm seeing a pattern here, I think. I'm going to try it one more time. When n is 4, a sub 4 is equal to a sub 4 minus 2 plus a sub 4 minus 1, which is a sub 2 plus a sub 3. Yep, it's happening. I see it. That's 2 plus 3. That's my two previous terms. My last two terms in the sequence that I've created get added together to give me a 5. That's my pattern. Here's how it started. 1 and 1 added up to be 2. Then 1 plus 2 became the 3. 2 plus 3 became the 5. If you see that pattern, then keep using it. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is going to be 21. 13 plus 21, and so on and so on and so forth. That's what we call a recursive sequence. The next term depends on two or more of previous terms. Our next special sequence is called factorials. And factorial notation is when your n variable, it has to be positive integer, and you're going to use an exclamation point next to it. That's called a factorial symbol. What that means is that you start at the end, and then you multiply it by the next positive number smaller than n, which is n minus 1, then n minus 2, all the way down till you get to a 1. We have two special cases. 0 factorial is 1, and 1 factorial is 1. So if we wanted to start creating your factorials, which is a good practice because you should probably memorize some of these numbers. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial, wait a minute, there's 3, 2, 1 again, just like I had here. So when I have 4 factorial, you can take the answer you had in 3 factorial, which is 6, 3, 2, 1, 3, 2, 1, and multiply it by the 4, 24. So 5 factorial will be 24 times 5, which is 120. 6 factorial will be 6 times 120. That's 720. All right, so write the first 5 terms given by a sub n equals 2 to the n over n factorial, where n, if they change it to a 0, then okay, we start with 0. So when n is equal to 0, a sub 0 equals 2 to the 0, which is 1, and 0 factorial, which is 1. So 1 over 1 is 1. So that's your first term, even though it says a sub 0. So we're only going to go up to when n is 4. So when n is 1, a sub 1 will be 2 to the first over 1 factorial. So 1 factorial is 1, so that's a 2. A sub 2, 2 squared will be 4. 2 factorial was 2, so 4 over 2 is 2. A sub 3, 2 to the third power over 3 factorial, so that would be, what, 2 to the third is 8 over 3 factorial 6, that reduces to 4 thirds. And finally, a sub 4 is 2 to the fourth, which that will be 16, and 4 factorial is 24. Reduce that, and we get 2 thirds. There's my first 5 terms. Now, you can simplify factorials by hand probably faster than trying to enter these into the calculator, and I'll show you where that factorial button is. But I've found that it's quicker to do these by hand. And what I mean by that is look for the biggest integer factorial, 8 factorial. Now look in the denominator. What's the next biggest n factorial? 6 factorial. You take the 8 factorial, you start counting backwards, 8 times 7 times 6, which is now the same as this 6, so just write it as 6 factorial times 6 factorial. My question to you, why write out 6 times 5 times 4 times 3 times 2 times 1 on the top, and on the bottom 6 times 5 times 4 times 3 times 2 times 1, just to cancel them out? That's a waste of time. The smaller 2 factorial, we'll write that out, and we'll start to cancel. So 2 can go into 8 4 times, and the 6 factorials are identical. We'll cancel those. So 4 times 7 is 28 over 1. That's my answer. Next example, follow the same procedure. Find the biggest factorial, 6 factorial. Go to the bottom, who's the biggest? 5. Match those two up. So that's going to be 6 times 5 factorial. Leave the 5 factorial alone. Those are done. Now, who's left? Well, we got 3 factorial down here. We're going to count down until you hit 2 factorial. So 3 times 2 factorial. Leave the 2 factorial alone. We're going to cancel those. 6 times 5 factorial. Stop. We're going to cancel the 5 factorials. Boom, boom. And then, whoops, then the 2 can go, or excuse me, the 3 can go into 6 twice. So everything on the bottom canceled out to a 1. Your final answer here is a 2. And even if they don't give you numbers, we can still clean this up. And I don't know why my little factorial button symbol is hiding over here by the parentheses. But this would start out as n factorial on the top, count down, n times n minus 1 factorial with the n minus 1 factorial on the bottom. We can cancel those. The answer is n. Now, the next thing we want to do with these sequences is we want to start adding all these terms together. This is called summation notation. You're going to get this big Greek-looking letter E. It will have a variable on the bottom. In this case, it's a k. This is called the index of the summation. This is your counter. 1, 2, 3, 4, 5, all the way up to n, which is your upper limit. And so that tells us how many terms we have to create, and we add those together, and this is, if you will, your sequence function. So if we had to find the summation of these two expressions, we have to add, when k is 1, 2, 3, 4, all the way up to 5. So we're going to plug this in. This would be 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. So 3 plus 6 plus 9 plus 12 plus 15, add that all up, it's 45. And we don't have to start at 1 on the bottom. You can start whatever they ask you to start at. So we're going to start with 3. So that's 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus, to the upper limit, 1 plus 6 squared. So 9 plus 1, 10. 16 plus 1, 17. 25 plus 1, 26. 36 plus 1, 37. Add it all together, you get 90. You can also work backwards. They give you a bunch of terms added together, and we're going to write this in summation notation. So what I'm looking for here is, okay, the 2's and the power stay the same. So that's probably your variable k being squared. And then we start with a 1, change to a 2, a 3, a 4, all the way up to 9. So my lower limit is 1, so k equals 1, up to my upper limit 9. And okay, we're done. So again, the 1, that's your lower, the 9, that's your upper, and there's your summation notation. Now, if this one says 1 plus 1 half plus 1 fourth plus 1 eighth, we got to look for a pattern in our denominators, because the pattern in the numerators stay 1. We can see that right there. So this will treat this as 1 over 1. So I need to say k is starting at 1. And well, no, not 2, 4, 8. It's got to be something different here. So let's see. K is 1, that's this term. When k is 2, that's this. When k is 3, we get 1/4. When 4, we get an 8, all the way up to when we get to n. So we can say this is 2 to the 0 power is 1. This is 2 to the first power. Break 4 down to 2 squared. 8 is 2 to the third. And if you notice that all these exponents on my 2 are 1 less than the k. So therefore, this is n. If these k values are 1 bigger than the powers on your 2, then 1 bigger than n minus 1 is the n. So this summation is going from k equals 1 up to n of 1 over 2 to the k minus 1 power. I got to take out the n because that's our upper limit. So we're going to have to switch that out with your index counting variable of your summation symbol. So again, there's your 1, there's your n, we got it done. Now, technically, these could be really, really ugly. I mean, if they took this first one here and said k equals 1 to 50, I really have no desire to find 50 numbers and add them together. So there's some properties of summations that we can use to make things quicker and easier. So here, if you're taking the summation of just a constant, it's automatically this constant value times n, but it has to start with 1 on the bottom. Over here, if you have a constant being multiplied to your function, well then don't make the numbers bigger. Factor that constant out to the front of the notation, use your function, find that sum, and then multiply by c after that, and you can work with smaller numbers instead of larger numbers. If there's 2 sequence functions, you can write them as 2 separate summations. Same with subtracting. And number 5 here, this looks really confusing, and I think I'll come back to this one. But this one's one that we use when your k doesn't start at a 1. If you notice, every summation symbol has 1 in the bottom for your starting number. Number 5 is the one we use when we don't start with a 1, and I'll show you how we get to that. It's easier to look at an actual numerical example. 6, 7, and 8. These are nice. If you're taking the summation of a linear function, k to the first power, that means 1 plus 2 plus 3 plus all the way up to n. So if this was like going up to 50, if that was 50, I'm not going to go in my calculator 1 plus 2 plus 3 plus 4 plus 5 all the way up to 50. You can use this formula. N, which is this n on the top, 50, times the n plus 1, the next biggest value would be 51, and then divide that by 2, you have the sum of all 50 terms. So this is going to be very helpful. And we have a formula for when you have k squared. Again, I would not want to do this if I was going up to 50 terms. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, all up to 50 squared. No way. So this formula is the n times the n plus 1 times another binomial 2n plus 1 over 6. And people always ask me, how do you memorize all these formulas? Well, look, here's n times n plus 1 over 2. That's locked in my brain. So when I go to k squared, notice I have 3 n's. When it's k to the first, I have 2 n's. You always have to have one more n in the formula than you do on the power of k. So since that's k squared, I need 3 n's. How do you remember this binomial? Look, I have 2 n's with a plus 1. Oh, there's the third binomial right there. How do I get to 6? That was 2. I now have 3 factors on the top. 2 times 3 is 6. That's just a quirky way of me remembering it. We have another one formula for k cubed. 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. Again, if I had 50 terms, I'm not going to find up to 50 cubed and add these together. Here's the formula. This one's really nice. It's k to the third, so there should be 4 n's. 1, 2. Oh, wait a minute. Oh, I'm squaring it, so that means that's n times an n, and an n plus 1 times an n plus 1. There's my 4 n's. Well, wait a minute. This is exactly the same is when k was to the first power. So when k is to the first power, then I jump to k cubed. I just square the k to the first formula. But all those properties start with k equals 1 and they end with some n constant value. The only one that's not like that, we start off with some other number than 1 on the bottom, but we're going to force it to be ones, and I'll show you how we do that. Alright, so here was that summation. There was the 3k, but now we're going from 1 to 10. Well, I'm going to use some properties. N is my 10. This is property number 2. Back here, I'm going to give you the property numbers. And so 2 means we're going to take that 3 and factor it to the front. So 3 times the summation of 1 up to 10 of k to the first power. Okay, property number 6. We can use this formula and just put 10 in for those two ends. And we can find the sum. So this is 3 times n times n plus 1. Well, 2 can go into 10 5 times. 10 plus 1 is 11. So 3 times 5 times 11, 165. That's a lot faster than trying to add up 10 numbers. Next example here is k is equal to 1, so we can use our properties. This is property number 3, where you separate the two terms into two different summations. And then I can use property number 8, k to the third. That's the n times n plus 1 over 2, all squared. And then here's your constant. All right, this is going to be your constant c times the n8. That's property number 1. So all we have to do is crunch these numbers. Well, to simplify this out, 2 can go into 8 4 times. 8 plus 1 is 9. So this will be 4 times 9, which is 36. And we square the 36. And then we'll add an 8 to it, which came from 1 times 8. So that's 1,304. Next, oh, holy cow. How would you like to find 24 numbers based off of trinomial? No. Let's use our properties. I have 3 terms. I want 3 separate summations. One summation for k squared. Factor the minus 7 out in front. 1 for the k. Constant number 2. And now I'm going to go use all my properties. I'm going to use the k squared property, the k to the first, and my constant. So k squared was n, which is 24, times n plus 1, that'll be 24 plus 1, times the binomial 2n plus 1, so 2 times 24, all over 6, minus 7, k to the first, n, times n plus 1 all over 2, and then your constant is just the constant times the n, 24. So 6 can go into 24 4 times. 2 can go into 24 12 times. So we have 4 times 25, 24 plus 1. 2 times 24 is 48 plus 1 is 49. Minus 7 times 12 times 25 plus 2 times 24. I'm sorry, hello calculator. Multiply this all out for me and subtract and add. Thank you very much. 2,848. We're done. Okay? Now, notice that this one doesn't start with a 1. So that was property number 5 that we were talking about. Okay, so what I need to do is I'd love to be able to separate this out as 4 times the summation of k squared and use my formula. But because we don't start with a 1, I can't do that. I can factor out the 4, but I want to use that formula. So here's what we're going to do. I'm going to break this down and make this summation right here start at 1. Now wait a minute. That's k equals 1, 2, 3, 4, and 5. That's 5 extra terms I'm adding on. So what do? We subtract off the first 5 terms. So this is the all 20 terms. I only want 6 through 20, which is 15, so I subtract off the first 5. And now I can use my formula. 4 times, we'll have the 20n times 20 plus 1, n plus 1. Here's the 2n plus 1. Minus, now for this one, n is 5. N plus 1, 2n plus 1, 5, 5 plus 1, 2 times 5 plus 1. So crunch the numbers. Now I did that because I noticed, wait a minute, this 6 doesn't go into 5, so I need to simplify these numbers. This 6 will factor in some way, shape, or form into what's ever in the top. So the second one here, you can see 6 and 6 will cancel. But over here, I'm going to have to break my 6 up into 2 times 3. So 2 can go into 20 10 times. And the 3 factor in 6 can go into 21 7 times. Now the 6 is gone. Here, like we said, the 6's cancel. So 4 times, in parentheses or brackets, 10 times 7 times 41 minus 5 times 11, close your parentheses, that's 11,260.